Hello everyone, my name is Gabriel Bowler, and today I'm going to be talking about concrete hydration process. So an overview, I'm going to be going over introduction, components, procedure, phases, compounds, properties of concrete, summary, and then references. So concrete hydration is the process by which cement, sand, and gravel mixes with water to produce the concrete that we all use. The reaction with water is termed hydration. This involves many different reactions, often occurring at the same time. As the reactions proceed, the products of the hydration process gradually bond together the individual sand and gravel particles and other components of the concrete to form a solid mass. So first, I'll be going over the materials that make up concrete. Cement will be the first material I'll be discussing. Cement is a binder, a chemical substance used for construction that sets, hardens, and adheres to other materials to bind them together. Cement is seldom used on its own, but rather to bind sand and gravel together. Portland cement is the most common type of cement on the market. And pictured on the right is a picture of just what that would look like if you were going to buy it in a store. So next, I'll be talking about fine aggregates. Sand is the most common material used. It's the grain skeleton of concrete. Fine aggregates are essentially any natural sand particles won from the land through the mining process. Fine aggregates consist of natural sand or any crushed stone particles that are 1/4 inch or smaller. This product is also often referred to as 1/4 inch minus, as it refers to the size or grading of the particular aggregate. The majority of the volume in the formulations for making a concrete mix is taken up by these fine particles. It serves as a structural filler. You're able to have a substantial influence on the output by modifying the makeup of the fine aggregate, as well as its geometry, size, and other characteristics. Fine aggregates help the mixture to sustain its dimensions. It also has the potential to affect both the elastic properties and the damage tolerance of the concrete. And finally, the characteristics of the fine aggregates have a considerable bearing on the degree to which a concrete will shrink. And pictured on the right is just what that would look like. Now moving on to the coarse aggregates. Concrete aggregates should have a strong bond with the hardened cement paste. It should not interfere with the cement hardening and should not have a negative effect on the concrete durability. This portion of concrete is usually made out of gravel and pictured on the right. All right, so this picture demonstrates the different sizes of aggregates and helps you get a better grasp of the topic. Starting at the very bottom, we have our larger rocks. These are most likely not going to be used in concrete. However, moving counterclockwise a little, we get into the coarse aggregates that will be used. Then we continue moving counterclockwise and we get into our fine aggregates, which look like sand at the bottom left. So now moving into the last ingredient of the concrete process, water. Water is the key ingredient, which when mixed with cement forms a paste that binds the aggregate together. The water causes the hardening of concrete through a process called hydration. Hydration is a chemical reaction in which the major compounds in cement form chemical bonds with water molecules and become hydrates or hydration products. The amount of water in concrete controls many fresh and hardened properties in concrete, including workability, compressive strengths, permeability, and water tightness, durability, and weathering, drying, shrinking, and potential for cracking. For these reasons, limiting and controlling the amount of water in concrete is important for both constructability and surface life. The ratio of the amount of water minus the amount of water absorbed by the aggregates to the amount of materials by weight in concrete is called the water cementitious ratio and is referred as the WCN ratio. This is used to determine the amount that is needed. In general, less water produces better concrete. However, concrete needs enough water to lubricate and provide a workable mixture that can be mixed, placed, consolidated, and finished without problems. So this is just a diagram of what the process of making and working concrete looks like. At the top, you can see the materials that I've already discussed. You have your cement, sand, fine aggregates, coarse aggregates, and water. These are collected and the amount is determined to properly mix it. Then the mixing occurs. This is the process that I'm discussing today. The slump test is not part of it, but the concrete slump test measures the consistency of fresh concrete before it sets. It is performed to check the workability of fresh-made concrete, and therefore the ease of that concrete flows. It can also be used as an indicator of an improperly mixed batch. Then the concrete cube test. This is performed for the purpose of determining the compressive strength of the concrete element. Then after that, the concrete is transported, placed, and compacted. So now moving on to the hydration process in concrete making. This graph shows what it's going to look like in the temperature changes. I'll be discussing the 5 phases later in this presentation, but looking at the graph right now, you can see a lot of temperature changes. Right off the start, the temperature rises drastically and then cools off for a bit until it reaches around phase 3 and continues to rise again. Then once it gets to phase 4, it starts to cool down until phase 5 where it steadies out. This is another chart that shows the hydration process. What is different about this chart is that it shows the time in each phase. The first phase only takes around 15 minutes. The temperature is able to increase a lot in that short amount of time. The second phase takes around 2 hours. The third phase is a bit longer and will take around 12 hours. Then the fourth phase takes around 20 hours. And lastly, the last phase, the fifth one, that can take several days. So moving on to the phases. So this is the pre-induction period. After mixing the cement and water comes into contact with each other, a peak in temperature happens. The aluminate reacts with the water to form entrigite, which is the aluminate hydrate. The release of this energy of these reactions causes the initial peak. So in phase 2, this is the induction period. A result of the reaction described in phase 1 is a surface coating of the cement particles. This coating keeps increasing, but also doesn't slow down the reaction, as the access to water isn't as good as when the concrete is mixed. The amount of hydrated concrete helps increasing on a steady level while the surface of the concrete keeps fluid. This phase is used for transporting and pouring the concrete. As the concrete stays on a fluid level, the length of this period depends on each individual concrete mix and can. Therefore, be optimized depending on the application of water, concrete, length of transportation, and more. This phase ends with the initial set of the concrete. So this is the acceleration period. A heat increase happens due to the reaction between calcium silicate, which creates a silicate hydrate. The creation of this CHS also has a major impact on the concrete strength during this phase. In the case for example mass concrete application, it can be very important to monitor the internal temperature variances, as the concrete temperature during this phase can increase rapidly to reach internal temperatures like 70 to 80 degrees Celsius. It is normally not recommended to exceed temperatures around 70 degrees Celsius. So this is a deceleration period. A maximum temperature has now been reached and the availability of free particles is now reduced and therefore slows down the temperature increase. This phase often ends with the desired strength and the formwork around the concrete can now be removed. Monitoring of concrete maturity and temperature and therefore enables the user with the exact time where this is possible. So the last phase, the diffusion period. The hydration process is now slowed down and will continue slowing to finish the remaining available cement and water particles. The formwork is now often removed and the concrete will now, over time, finish the hydration process and reach final strengths. And this is just a chart that shows the compounds of cement. So the first one is tricalcium aluminate. This is around 10% of it. Then the tetracalcium aluminofurate. This is about 8%. Then the belite, that's around 20%. And then the alite is 55%. And then the sodium oxide and the potassium oxide are up to 2%. And the gypsum is around 5%. So moving on to properties of concrete, the first one is compressive strength. Compressive strength is the ability of material or structure to carry the loads on its surface without any crack or deflection. A material under compression tends to reduce the size, while in tension, size elongates. Compressive strength of concrete depends on many factors such as water-cement ratio, cement strength, quality of concrete material, quality control during the production of concrete, and even more. Concrete compressive strength for general construction variances from 2,200 psi to 4,400 psi and higher in commercial and industrial structures. Then the tensile strength. The tensile strength of concrete is also a very important parameter that is considered in the design. It can make a significant impact on other strengths of the structural element and flexure, as it is about 10% of concrete compressive strength. Concrete element subjected to pure tension or combined effect of compression and tension. A concrete column used to hag a floor can be considered as an example of pure tension. Flexural strength is one measure of the tensile strength of concrete. It is a measure of an unreinforced concrete beam or slab to resist failure and bending. Flexural strength is about 10 to 20% of compressive strength, depending on the size, type, and volume of coarse aggregate used. The shear strength of concrete is defined as its ability to resist forces that cause the material's inner structure to slide against itself. This can be measured either horizontally or vertically by seeing if a force causes object's layers to slide in a horizontal or vertical direction. Alongside compressive and tensile strength, the shear strength of concrete is essential for ensuring that the material is durable and resistant to a certain level of force. These factors play a big role in defining the quality of the structure as well as its longevity. In mechanical and structural engineering, the shear strength of concrete plays an essential role in ensuring that compounds such as beams, columns, and bolts are designed safely. And now, summary. So concrete is everywhere. Take a moment and think about all the concrete encounters that you've had in the last 24 hours. All of these concrete structures are created from a mixture of cement and water with the added aggregate. Water is a key reactant in the cement hydration. The incorporation of water into a substance is known as hydration. Here are my references, and that concludes my presentation. Thank you.